I will continue my last topic, and it's called linear algebra. Last time, I talked about the vector space and the linear transformation. And the special situation is when the transform in the same space is we call the operator. Last time I said if in the two vector space, this represent the linear transform. This two is a vector space, and this have dimension n, this have dimension m. The linear transforms can be represented by a matrix or a group of matrix. And if we select base for every vector space, for example, in V we select the base of Vn n. And in W we select the base W1, Wm. Two vector space, then we can represent the linear transforms like this. This matrix, and in the last class I also told if it is an operator and W is V is equal W, and select the same vector, same basis, W1 equals V1, and we call this an operator, and this matrix is square. And I also proved that if we can choose some basis to make this this matrix as upper triangle matrix, like this one, this matrix, and just some vector space, and I proved the existence. And also, I will define the matrix of this. I want to written as this. If this linear transform is T, and we choose the linear space of linear base of n, and m. As this is equal to this that A, and this stands for the matrix depends on the base you chosen. And if the two transforms we compose the two transforms together. The first transform is LV to W, and the second, the T is L W to U, and this matrix is A n by P, and this matrix B, and this matrix is A P plus M. And we can see that this matrix is defined linear transforms from V to U, and the dimension matrix is n plus n m, and it's matrix, and we suppose they select the same base V W U fixed. Now this matrix I will use C to represent its n, not m.
Excuse me. N is the transform.
L.
And
L stands for linear transforms. This it belongs this linear transform. If all ST is belong to this linear transforms, and if S belong to this linear transform, it belong to this transforms, and so TS is belong to this transforms, and all transform have matrix. Yes, so it's very straightforward. It can be proved that this two. This metric is C is M plus N is equal to A multiplied B, and they decompose together. And last time I also said I also proved that the linear upper triangle matrix is very attractive property because it makes matrix very easy to manipulation and implementation, and we see that this matrix can be improved like this one. And this is that I said this is an operator because for the triangle matrix it must be the square matrix, and if it satisfies this property and the matrix is upper triangle, I mean this one is equal this one plus the first elements, and so I only have its upper scalar part. So if I have these properties from G to N, it will have upper triangle matrix. So this is just the summation of the last class. And also, I said in last class some ion value and ion vectors properties, and I will prove that if if W is equal, we short as this one, and if lambda 1 and lambda m are distinct vector values, and V1 are their correspondent vectors, then these vectors are independent for if their ion values are distinct, different, and I'll prove it. How to prove it is that because the ion values must be non-zero, I can choose from the first one to from left to right. If I find someone Vn makes this linear, for example, lambda is n value. We is the corresponding n vectors.
Oh, and what's lambda?
It's lambda.
lambda, what is lambda?
N value.
Eigenvalue.
N value, yeah.
Eigenvalues.
this one?
Yeah, eigenvalues.
Eigenvalue, okay. Eigenvalues. So I can find some vector because the most big vectors can be represented as this one -1. This is n, not this thing from M, maybe not M, distinct M. And if I found some vector from that one, I found some dependence relation, can represent like this. And I use some linear properties. For this, where I found that is V1 to V -1 is independent, and when we plug in Vn, they are not independent; it's dependent. So Vn can be expressed as this expression, and I use some this linear transforms to this, and have because it has additive properties and homogeneous properties, and can be expressed as this. And because this is n values, so it can express as n vector as this one, and this one is equal to this one because this. And this vector I can multiply this expression as lambda n to this lambda n, and also this all lambda n, all multiply lambda n. Then I subtract the two expressions, and this two is equal, and this is equal 0, and this one is equal v1 lambda 1 lambda n, and v1 a minus 1 lambda minus 1 and lambda n. Minus 1. Oh, it's like this one, and the two-way subtraction. And because they are all distinct, so all the n value subtract must be non-zero because they are so and also these variables are independent. So a1 to a minus 1 must be 0. If a1 and a minus 1 must be 0, then Vn is 0. Vn is 0 is contradiction. So this assumption is not validated. So all the variables are independent, correspond different n values. Oh, okay. In fact, if we can write the linear transforms or operator as this Vn lambda 1 to lambda n, this is the diagonal matrix, and I think this matrix is beautiful, and this n value may be equal or not equal. So based on my previous assumption, the n vector space can be decomposed like this one. n because I suppose to have m independent m values. And so all the m values in this space and uniform is the base, and they are all independent. So we can write as a direct sum based on their distinct values to divide this vector space. So this is it's a beautiful side of m value. And this part is the last left. V is a vector space with a dimension n. Vector space.
Okay. I guess you want to use different notation. I mean, like for it's a vector. At least you want to write it square.
Yeah, I think it can write as diagonal matrix. I mean.
Yeah, I mean your notation is how. Your V sounds like it looks like just a vector. Maybe you want to use square notation.
Yeah. If I write like this, V is the base.
Yeah, V is basis.
Yeah. Now from this, we also can V1 Tv1 is equal lambda 1 V1, and also Tvn is equal lambda n. Because base is not a zero vector, so it's non-zero. Also V is non-zero, and so it's an m value and m vector.
I'm not sure. Your T is a.
T is the linear transforms.
Yeah, so I how do you define the direct sum here? So each of this would be a base, each of the is a subspace, right? You assume that each of T minus of the I.
Yeah,
that is subspace, right?
M vector must the subspace. Yeah.
Yeah.
Because I can prove it.
But I mean, how do you define this?
I don't write the null space.
Pick another there.
Sorry, I missed the notation. Null space.
Yeah, I mean that is ridiculous. Right?
Sorry. You mean this one?
Yeah, something like that.
Yeah, the null space because m vector is in this null space. Yes.
Okay.
Any questions?
The T minus lambda R is a null space.
This thing?
What's the null space?
This thing?
You need to define null space for that.
Yeah, null space. I will go. If this way from 0, and I also proved that last class is a space. This is null space. This is a ring.
What is more kind of reckless location, like concept location and so on?
Yeah. And
no, I mean, can you divide it in more reckless location, like set location and so on? So it will look more like long T is equal to whatever the set of something.
you mean null, right?
Yeah, it's that.
You mean how do
No, just write it out, like the null space definition or
null space?
Yeah, all reckless location.
For linear transforms and from I said the general definition. Linear transform. This is requires all the linear transform from this vector space to W, and the T is belong to this vector. Belong to this vector space among the component, and
that no, that in that equation, which one is the null space? The T?
This
Yes.
one. This one is this who
whole
operator.
thing.
Who operator? Because ion value.
Yeah.
Okay, this part. Any other questions? Oh, and I complete the linear independent part. Now I will use more tools to research or study the vector space, and we will define the operation like inner product and outer product. And the inner product is defined like this one. We first also use the should also define the vector space V, and it's by operation. Have to operate, and V W is equal to W, and this operation will be like this one, and it's scalar. This operation is scalar and have some properties. First property is this one, very important property, and the zero is satisfies if and only if V is the zero vector. This vector maybe not, and also have additive vectors. And also I have a U. And additive. Conjugate transpose, conjugate symmetry, like yeah, this property very important. All the properties are very important. And from after I define this property, it's very easy to show that. Is equal to this one, and equal this one. Very straightforward. And after define this inner product, this is inner product. Also in mathematics, also have outer product.
That one is A bar?
This one?
No.
This one?
Yes.
Oh, it's conjugate.
No. This.
This one?
Yes.
Oh, also conjugate. Yeah. From this one.
Oh.
And if we can write the inner product as this one, and for example, we often use this define some inner product in mathematics, and if they change the position, it's outer product. And we can show that inner product is the trace of outer product is matrix. The inner product is scalar, and the inner product is this inner product is also in real space of that one. And it's the trace of the matrix of outer product space. Very easy to prove. Not bad. Not problem. And if two vectors is equal to 0, I said they are orthogonal. This notation orthogonal. And let me see next. Also, is if two vector is orthogonal, I will write like this. It's kind of easy to prove. Okay, I will define another matrix norms, and it's equal to this one. Its norms, this norms is more general, maybe a more general mathematical concept. But in inner product, I suppose it's this one, and it satisfies the three properties of norms. Also, symmetry of the triangles is relevant. And if V is the orthogonal W, then we can prove that. It's called it's a Greek mathematician's theorem, maybe more than 2,000 years ago, and very straightforward to prove it. This one equal this one, and down. This multiply is 0, so they all disappeared after this one, so it's satisfied. And also I will prove a very important theorem called Cauchy-Schwarz equalities, used very commonly in mathematics. It's like this one. Maybe if I'm familiar with this equalities, I will prove it's more general. You can be expressed as this one. This two is the same. This expression and this expression is orthogonal. You can it's pretty straightforward to using this one to the one, and this is disappear and disappear, and they are same and
You have U inside?
What?
What's that? U right after that?
minus.
Okay,
It's
and
a
this in
parenthesis.
there for
No, it's parentheses, yes.
Yeah,
It's
it
a
is bracket.
It's parentheses.
Yeah, this together, these two parts. These two are orthogonal. Yeah.
I thought this one is the inner product, yeah.
Yeah, this are orthogonal. I also I just said the two orthogonal have this properties. Yes. And this is this value is greater than 0. Or equal there, non-negative, yeah. So because it's a scalar, this is scalar, I can drag it out of the norms. This is scalar. And out, and left just the norm V. Square, yes. This one is yes, and after square is 4, and this left of this side, so this is 2, so this becomes 2, and this is disappeared, and this one.
What is that one? The first one is a door?
This one?
Oh, what is the
Absolute value.
is that the value?
You mean this one?
Yeah.
Absolute value. Because it's scalar
Yeah.
value only, absolute value. And multiply this to this side and becomes yes. So we will use square because
Basically, this you tear your third equation is from the second one.
this one,
No, the third one.
this one, this
Okay,
one.
yes.
Yes, this is equal to this one.
No, that one is from the second one.
Yes, because they are orthogonal. This is
Oh.
very orthogonal. It's from the ancient Greek series. So just prove it. And so we can prove this one. And for the non-negative, the square can all disappear. So this one. And very straightforward to present this one. Yes, I have proved this theorem in general. And as a matter of fact, you can, because I suppose V is non-zero, you can suppose that this equality is satisfied when U is some V or V some U or like this one. They are parallel, but they are all direct or maybe different.
Excuse me. Well, that one is the inner product of the V and V, not U and V.
This is V.
No, the fourth.
This.
Yeah, I mean, I'm talking about the last one, the last equation. The last one.
This one.
Yes.
Yes, UV.
This one is from the previous.
Yeah, previous.
Okay. For that one is the inner product of the V and V is bigger than U and V. Yes?
So you mean this inside bigger?
No.
No. This one is the norm square. Yeah.
Yeah.
This square and this is 4 power 4 and this is square and after yes.
Oh, okay.
This is the left square. So just square is equal to this one. And we expand this expression can be write as this one. This stands for the real part of this inner product space. And of course it is less than this one because it's considered the major part, so it's bigger than this one. This is absolute value. And from my last proof, the Cauchy theorem, also this one is less than this equation. Yes. So this is a perfect square. Perfect square. So this one is this one and this theorem after they are square root. And also, if we have a base, for example, independent vectors, I want to make them some perfect. Now we have some tools to make them orthogonal, and this is called one method. Is Graham-Schwarz theorem. We all learned the class. It's written like this one. Trust the theorem as this one also. I norm all the vector space, not just make the orthogonal, also make the unit vectors for every one. So the auto class can be after I get every orthogonal parts, I also normalize them. So this vector space has these properties. So if
I didn't you write down the EN.
you mean this one?
No, the whole thing. Yeah.
This one?
It. Yes.
Yes, it's Vn.
What's the VN?
It means the inner product is, for example, I will already normalize so many vector space. I will subtract every scalar, every sub values in every spaces. This is the value, and this is that vectors. So we subtract this one. It does not have the part of the one, and this the subtract 2 or until 2 and minus 1.
With the of the previous E?
E1. Yeah, E1, E2, E3. This is the general
the
expression.
definition of the En. Yes.
Yeah, this one.
Yeah.
Yeah, this is the definition. All the algorithm to make this. Yeah. And from this one, and I found the after linear independent alpha function. It's very easy to prove that this property is the span of E1 and En. Or I use M. And V1 for M equal 1 and you can find this one very straightforward because it from V1 is that space is very equal to this from 1 to n. Yeah. Use this we can prove very important properties because what I already proved is that I can find a base for a vector space. I can find a complex vector space. I can find a base to make this vector space and the matrix at the upper triangle. So yes, that's the proof. That's that proof. Now I also proved that I can have the orthogonal vector space and this property. We know that if it belongs to this subspace J from 1 to n, then use this space, we can express the linear transform as the upper triangle matrix. And also from this properties we see that we can prove that for each Tvj this belong to this, because it's from this Vj, it belong to span Vj span 1. So which means this orthogonal vector base also have this property. And so I can find orthogonal vector base, orthogonal basis to make the matrix upper triangle. Not only the general base, also this orthogonal basis. So this can become orthogonal basis to make this matrix upper triangle. It's very important. Remember that I will clarify some motivation is that if the vector space is from E1 En vector space, and we can express at this one. And its projection in every subspace subvector can express at this one very easy. And all the orthogonal are orthogonal. So that's this part. The introduction of inner product space. vectors. If I define, I will define some notations. If I have a set S, maybe not the vector subspace, maybe not subspace, and contain some vectors V1 or infinities that are uncountable. That one, and if some vector is orthogonal, U is orthogonal, all the vector space Vj we now S said V is orthogonal to S. It's orthogonal. All you must orthogonal all the subset component. If S is subspace, if S is if W is the subspace of V, I mean it's subspace of V, then I can find a space like this one. I can it's very easy to interpret because for this vector space we can use this vector to make multiples of the full vector space of two dimensions. This one is also can use the orthogonal this one subspace and the direct from this is direct sum.
What do you mean by the W?
This one?
Yeah.
All the vector in W orthogonal, all the vector in this W.
What do you call it? W orthogonal? What do you call that one?
Yes, that's W orthogonal.
W orthogonal.
Yeah, this one very easy. Two parts.
W subspace of V.
Yeah, W subspace of V. Yes, and then I can prove it. Part two. If V, sub V is belong to V, and we can, so because it's subspace, yeah, subspace have maybe have some vector, yeah, this have base, this one must have some base, and so
I think my problem is the definition of W orthogonal. What's the definition of that?
and then we subtract all this part. They are two equal. I use the W. This one. Small W. Yeah, this is two equal. And it's very easy to prove that the two is orthogonal. For every V belong to V. So we can use.
What's the definition of the W orthogonal?
W orthogonal?
Yeah, what's the definition of that? Is equal to 0.
Yeah, orthogonal.
You never give the definition. You just assume they know. You didn't define that subjects of optimal, that means that the is equal to 0.
Just said this.
Yeah, I don't think you say that.
Yeah.
I mean, at least you didn't write it out.
Yeah. Is this clear? And so all the vector space can be compressed as two of them. And if yeah, this is some product of two space this one. one is that if we fitting some, I said some application. If we fitting for a polynomial, we use some polynomial to fitting some sine or cosine that algebra curves, and we also use this properties. And, just easy to recap. For example, if we the subspace is 1, 2, x5, we use cosine to represent as this polynomials. So we also do that we projection this part to every part here, and this one, and the projection of cosine x 1. Oh, sorry. I don't use this one. In this part must be first orthogonal, or the basis. This basis must be orthogonal first. I mean, define the 0, 1. This is inner product space. First must be find the orthogonal basis and projection the curves to the all orthogonal and find the part and use this as fitting scalars. This is some she's very easy. And now I will search on the transpose, conjugate transpose.
Really, I didn't get the last one.
This one?
The basis is 1, 2.
This vector is a vector space. It's 5. A1, A5. All the vector space. We must find some vector space and to have fitting this cosine x, or for example cosine x in this space. First, this may be not orthogonal in this space, and in numerical we also said find some. I don't remember actually. Maybe this is orthogonal.
What's the whole problem like step by step? Like, you just want to write the whole problem step by step?
These steps.
Yeah, what do you want to say? Like, you just.
Just mention is.
I mean, yeah, you just write the steps out like.
Yes, I just mentioned this part is that when one fitting in a subspace, we first find the subspace. In this subspace, find some orthogonal basis in this subspace, and then projection the vector space, project the vector space to the subspace space, and find the scalar and use this as this polynomial or other thing as the fitting result. Just this one, just the projection. What we do also is this to find in the numerical value. The first find the orthonormal basis. For example, S1 to S5. I remember you have some. We can find some numerical values to make them the basis.
So what are the bases here?
This basis.
I mean, what are the bases? Like, what's U and V here, or like U and like U transpose here?
Oh. U is I want the projection in U.
Yes. And to give
And,
an example, right? So
V
what is
is
your
the-
example here?
V is all the polynomials, polynomials space. And V is U is subspace of all the polynomial. V is the supplement of this space. And I want to find a vector, maybe in X. We know it can be used the Taylor series to express its perfect, very long polynomials. But I want to use short one. So as projection in the short space, just this one. First, so I must find the subspace orthogonal space, orthogonal. And if I implement, if we just use this space to grasp, and I have other space part, it will make the bigger.
Can you give some example for the basis of U?
Basis, I can. I said just I can do, but I can. Maybe you can refer some numerical value books. I just mentioned have some good polynomials.
You cannot get it given this example.
Yeah, I just said I learned in numerical value book, numerical computer books have this beautiful polynomials. You can refer to it. To make this under this one is orthogonal. Let's have this property, but this is not part of this one. I mean, I just emphasize.
Yeah, unless you just make everyone confused because you don't know what you're talking about. Anyway, just.
You want this polynomial?
I mean, if you give an example, you need to make it concrete, right? It's okay, we can leave it next time. Like that.
Huh?
I mean, we can leave this example next time, but I just mean like, what would give an example, just make it concrete.
Yeah, but find the orthogonal is I just remember is factorial can make this orthogonal. Some factorial is we can discuss it after. And if I can find the particles that for linear transforms from V to W, and I can find some orthogonal vector. I will define the linear function first. Linear function is like this one. This notation, and this belong to vector space. This vector space to a scalar. It's called a linear function, and it's satisfy linear property such as additives and homogeneous and properties.
From V to F.
Yeah, with F. F is scalar. Maybe C or yeah, this one. Yeah, this is vector. And I'll prove the properties that every linear transform, every linear function can be expressed expressed as this one. Can be expressed use this one for some W. And I will prove it. This is the basis also normal basis of V I can find. Then for vectors, it can be expressed as this. We express as this one. This form is equal to this form. So every linear function can be expressed use some W to express. And this is use some linear optics. We use here. And I put this in this one and I take it all together in this form. So this one is W. And all linear functions can be expressed like this. And also I will prove that this W is unique. Not only exists but also unique. For example, this. If this 2 is equal, now we can write is W1 is equal 0. Yeah, this one. And because V is the arbitrary vector in the subspace I use W minus W1. So this is equal 0. Yeah, I suppose W equal this one. It also must be satisfied. And from the so this can write as W is equal W1. Yeah, because this property I said in the inner product space when V is equal 0, it's multiplied this one. So W is equal. So we can find a vector. This vector is unique and exists in their transforms. Linear transform from L to W. This L to W and two vector from this two vector space and define this operation. you can see that this operation is linear, and also linear function because this is scalar. And if I fix, if I fix this one for v, actually v belongs to this vector space, it's a linear function. Because this is linear and all the inner product also have linear properties. And you can prove it very easily. So for a linear function, I already proved that there is existent some I use u can be expressed as this one. For some u, it depends on t and it's defined and the w is depend on t and just select the vector space. So we can write this one along this vector space because this vector is belong to W. So I found some this W space, U is W space, and can write this one to express this linear function. And already prove that this U is unique in last proof. So it's belong to, I can prove that this linear function is I use u is equal to this notation. I use this notation to denote the w from w to u because it's unique. It satisfies functions definition. The function is just from a vector space have only one to correspond with one. I just define this correspondence. And use this notation. So it can express that this one I call this operator a joint of this operator, a joint. And also I prove its existence. Yeah, in last proof I also prove existence. This is a joint. And yeah, they have very good symmetry properties. And first I will prove is that for some matrix I defined from V to W, V1, N, F1, F9. For a linear transform from V to W subspace, I can find two cases in correspond vector space, and they are also normal. And I find this matrix, define this matrix, and the component of Aij is equal to this one. Can just parallelize this one and be equal to this one. This is J, this is Y. This space is this one. And also W to V, and also have this vector from this vector space and use the opposite direction and define this matrix. I will say this matrix properties.
N by M.
Yes, N by M. Properties. I will see that they are transpose conjugate. For the Ji is equal to T star Fi Ej. Find this property. Pji must be equal to this one. And also the effect is equal to this one. The property can transpose together, and this one. And this is transpose because the two matrices is transpose. So AMN equal to, I use not to transpose and use conjugate matrix. We use the same base together. So now this property. Should I continue? After I said I completed the matrix spectrum decomposition. And if I want to say that if the operator have these properties, it's called self-adjoint. Self-adjoint. So this must be this operator from the same space and use the same basis from E1 to En. Yeah, this is also E1 to En, the same basis, and I define the self-adjoint. And self-adjoint have some properties. First is that their L value must be real. In this float, lambda can be here and is equal to V if it's N value. And this one, because it's self-adjoint, we know that T star V, yeah, is equal to this one. Because it's self-adjoint, T star is here, is equal here, is orthogonal operator. And because it's N value, and lambda V, and I put it outside, it must be conjugated in this position. So this one is equal to this one. Because the N value is non-zero, so this is bigger than 0 and bigger than 1, I can put this one. So lambda is equal lambda conjugate, so it's real. All the self-adjoint N value must be real. And also, I will prove that if TV equals 0, and T is the complex vector space. This is complex vector space. This is satisfied then T is equal to 0. 0 operator.
What do you mean by T is equal to 0? What do you mean by T is equal to 0?
T is equal. Yeah, this 0 is not a scalar. It's the vector. It makes all the operator vector space. For example, from to 0 vector. It's not scalar. It's vector. It's 0. I use this notation to mean 0 to this vector space for all v of that. That T is 0. This notation is said in the last class. Yes, this two for arbitrary U and W, this is equality.
I mean, you assume for all V, right? For all V, that will be V.
Yeah, all V. This is all V. Must satisfy all V. And this is multiply together is switch forward and equal this one. And we know that this can be expressed as V. This is V. Yes. So this is 0. This is also 0. This is 0. And this is 0. So this one is 0. Okay. So TW inner product of TU and W.
Can you explain again? Why is 0?
0?
Why that one is 0?
But because TV, this one, you can the whole part is V. You plus W is V. You can assume because this is satisfy all vector space.
And how about that term?
This one, this is the
That was inner product or not? The second term's inner product?
This one.
Yes.
Yeah. This is also this one. I have to use this one. If you multiply together, but I can see they are equally. So you can write down one step. They are equal to this one. So this is equal 0. I proved from this property. So because W and U is arbitrary, W is equal to U. So TU W is equal to 0 and T is 0. Okay, this is straightforward. So I prove this property, but it must be the complex vector space. If real space cannot satisfy this property. For example, in the two-dimensional space, if we make a rotation just 90 degrees, and the vector is orthogonal, and they are orthogonal, so they must be 0. But it's not a 0 operation, so it must be complex vector space. It's very important. I use I. Notice I can prove that if PV is belong to R in vector space, also T is belong to LV complex, then T is equal to T star. From very straightforward. Because if it belongs to R, then must be 0. Step by step, and color our problem will be the complex vector space that this is equal, then T minus T star is equal 0 must be protected, so we are equal to this property from us the zeros. And this is the steps. So for complex vector space, it can include all the vector satisfy these properties. The operator must be self-adjoint. And that's beautiful properties. Last, I will set a more general operator. This operator can express like this one. It's called normal operator. It's normal. Also defined areas. You can see that if it's self-joint, it must be normal. So joint is a special case because this one TT is equal. And if normal properties, if normal has these properties, this one, if this is satisfied, I have this one, and I will create. Before this theorem, after theorem, I will suppose a lemma, and after that, I will prove that lemma.
that one is equal to 0.
Yeah, this one equals 0. Which?
What do you mean by the inner product of something for all these?
This one?
Yeah. Is equal to 0.
Oh, yeah, equals 0. A equals can be proved in this direction, also in that direction, and you know this. And if it's normal, it can be like this one. And it also can express like this one. I will prove this is satisfied. Is that if T is self-joint, then TV is if TV this is equal 0, then T is equal 0. Whenever is the real or complex vector space even itself, this is satisfied at T 0. I will prove this lemma after this proof. And so suppose that is satisfied. And so this quality and the quality can be improved in all directions. And
TVB is equal to 0 and T equal to 0.
this one?
Yeah. So what was the difference from the reporting earlier on?
From this one?
Yeah, like earlier, isn't that you show something like TVB?
Because this is supposed in complex vector space. This is not have this assumption.
Okay.
And based on this, we can
The
have.
T now is not it's not complex.
Yeah, now it's not complex. Can be real.
Okay.
I did not suppose to be complex. So it must be this one. And so 0 so have this properties or weight, and after range we have this properties, and this can be dragged here and this dragged here, and we have these properties. So this is equal to this one, and also after this guy is equal to this one. So yes, sir. And if this is satisfied, this also is satisfied. Okay. I prove this theorem because very important. It will be used to improve the spectral decomposition, and also so I will prove this one. Like my last proof, if this satisfies and this one, we don't need to write the I part. The former is satisfied, and use the same argument. This is 0, this is 0, so this is 0. The same string value T equals 0. Have any questions? this multiply and subtract together is 2 tu w plus 2 w u and I must suppose it's in this one is a real space. This is in real space because it's more general than this one. I suppose in real space satisfy this condition. Real space. This one because in complex vector space I don't use the self-adjoint properties. I can straightforward do, and in real space I don't need to write the I part. So this one is equals to tu w and 2 u w tu. This one, and in real space this is equal to tu w equal this one. So the same property as common. So for self-adjoint, not only real but also complex vector space. Yeah, for real space must have the self-adjoint. For complex vector space, we don't need the self properties. I will prove two theorems. Last two theorems. The first theorem is that if alpha, beta are distinct eigenvalue, and V, W are correspond eigenvectors, I suppose T, and T is normal, I suppose. Now prove that these two vectors are orthogonal. Eigenvalue must be orthogonal if they are the eigenvalue distinct. that normal, the n value for the t, the n value also is t star the n value, n vector, and the n value is this is t star, and the n value is conjugate with each other. So if the two vectors correspond different distinct n values, I can express as this one, because this is also n value of t star, and this is n vector, and this is n value, so it can express as this one, and this can direct in the front, and this subtract this is 0, because this is distinct, so this is not 0, so this must be 0.
So what is that line below 0 for again, t minus lambda I b equals f4?
This one? You mean this?
Yeah, the whole line. Why we did that?
Oh, I want to prove that for normal, if this one is 0, this must be 0, yes, because they are equal. So all the n value belong to t, it also belong to t star.
Oh, okay. Are you showing two things now?
Yeah. I want to show this step. First, show this one. Because this use this from this to this use these properties.
And how you it's a silly question. How you write it down? Alpha minus beta is equal to that one.
Okay, I already proved that if it's normal, it must be equal. I will prove it. Yes, and if t is normal, this one is also normal.
My question is the first
This one?
Yeah, how do you write that?
it down?
Oh, I multiply the apart. This is alpha. I can the inner, and this beta. I use the last one, and it's complicated.
Why can't
You don't know this one?
no, why? Is it,
Why?
why is it conjugate of the beta?
This one?
Yeah.
Why this one?
Okay,
Yeah.
you put it in the second one.
Yeah, because yes.
Yeah.
Yeah, this must be complicated. This one, this one, or this one, 0, and it's distinct, so V is also W. So this can write n values, this n vectors, n vector correspond distinct values are orthogonal. Yes. Last I want to prove is the last topic is spectrum decomposition. It's I divided into parts. The first is for complex vector space. For complex vector space, if is t is equal t star normal, then I can find a vector space that's this one. This is the orthogonal space. Diagonal. In diagonal matrix, I can find it. This matrix diagonal. This is called spectrum decomposition. And all zero. Only have n value. We can see that this is all of this basis is n value and n vectors, and the scalar is the diagonal is and values. So, at first I will prove, I will see that they are equal. First, use a vector space of complex. And if we have these properties, we can easily to prove this one. It's very easy because the diagonal matrix, and also you prove that T stars matrix is equal to because it is the transpose conjugate of this matrix. I proved the previous. So all the two matrices is diagonal. So they must be communicated with each other. So it's very easy to prove this property from this.
Could you step by step for this one?
This step?
Yeah.
Okay. So this means that for arbitrary vector, this must satisfy this means. Okay, if I prove this one, it's done. So I multiply this two operator first, this one, and this one, and this TV, and I suppose the matrix is diagonal first. So is T star also diagonal?
Okay, so T stars is diagonal.
This one?
The second one, because you're
The second one is conjugate transpose. I proved in the previous. So they're just conjugate. And so this one, and from this one, and this step by step, and it can also written as this one is scalar, and this is the space, and and I also proved that this is equal to all the matrices multiplied together to express this expression. So it's equal if you want to multiply this matrix and this matrix. This matrix is corresponds to T star, and this matrix corresponds to T. And because they are diagonal, if you change the operation, this will be here. So they will be equal. be equal change the position. Because the diagonal transpose diagonal and communicate. So this is equal and all of this equal. So all of this equal. So T is T star, V is equal to T star, TV. Okay. The difficult part is from this direction to this one. This is very easy. Okay, not difficult. I already proved that I can find a matrix to make his matrix upper triangle use some also normal basis. To make it clear. I have proved that I make matrix upper triangle for arbitrary operator in complex vector space. Make this upper triangle. That all of this is all 0. So the T star can be expressed as this one. Lower triangle use the same basis. Yes. Okay. And if it's normal, I prove if operator is normal, T is equal to T star and this one. I already proved that for arbitrary vector, this must be equal. For arbitrary vector belong to V, this must be equal. And so T1 is equal to T star E1, yes. And T E1 is equal to E1, this one. And from this one, E1, A1, I use Y. And this one is equal to this one is equal to this one after you multiply together. And they are equal, so these two are equal. Because this is it's used norms, so the conjugate can be erased. The two conjugates have the same absolute value, like this. And this is this period, so it's 0 equal all of this subvector. So all the vector here must be 0. The left norm. And because the E1 is all the E is also normal, they must be 1 after this subvector outside. This is equal to can, blah blah, you use the same property and use the TE2 equals this one, star E2, this property, and make this part 0, and one by one, all this. The second is only equal to 2 and all the this part is 0, so it's diagonal. Yes. So the two properties are equal with each other, and this is for complex vector space, and it's the necessary and sufficient condition to gather this one. And any question? For the real vector space, I just give you some hint. If you have interest, you can prove it by yourself. Its necessary, its condition is self-adjoint matrix diagonal. Diagonal. It's not normal, but even more condition is self-adjoint. And you must use some lemma to prove this one. That if alpha square is less than beta over 4, then this operator is inverse. If satisfies in real vector space, it satisfies this, and this vector is reverse and can inverse. Yes, inverse. This vector is inverse. No vector. The operator is inverse. This vector.
Is it vertical? You mean like?
Yeah, invertible. Did I prove it?
Yeah, I guess it's good to show.
It must satisfy this condition.